obviously. So yeah, okay. So today we're going to start with talking about equivalences and proving equivalences using known equivalences. In the last session, we proved equivalences using truth tables. Remember? So here at the start of this session, we will prove equivalences using known equivalences. What are these known equivalences? These known equivalences are the list of these equivalences, these obvious equivalences. Some of these ones that we've discussed or looked at the end of last session. Some of these equivalences, these are the important, some of the important, very important equivalences that you always need to remember. And how do you remember that? By more and more practice. These equivalences, and then finally these equivalences related to tautologies and contradictions and identities. Based on these, we prove certain other equivalences. So you might have expressions like this, one on the left hand side, other on the right hand side of the equivalency, and you'd have to prove it by using these list of known equivalences or these laws. Okay. So in the question or in some problems, it's not mentioned how you have to prove the equivalence. That is, if the method is not specified, then it's up to you. You can go with truth tables or logical reasoning or known equivalences, or that is the laws. It's up to you. However, if it's specified, that you have to use the truth table, then you have to use the truth table. If it's specified that you have to use known equivalences or you have to use Boolean algebra, the laws of Boolean algebra, then you have to use these known equivalences in order to prove a certain equivalence. Okay. So the way we do these things, we're using known equivalences, that we start from one side, then apply the laws, and then try to get to the other side. Usually we start from the side that looks a little more expanded. We'll start from the more expanded expression or the bigger expression to the more concise expression. So here, as you can see, the expression on the left hand side is the bigger expression, right? That is the more expanded expression of the bigger expression. From this one, it would be easier. It would be easier to convert this one to this more concise expression, all right? It's usually it's easier that way. So you look at both sides, the left hand side and the right hand side, whichever is the bigger expression, and you also at the same time think about the laws or the known equivalences, and you try to figure out, okay, which one is going to be easier, and start from that side. So for making that decision very fast and for being able to apply the equivalences very fast without having to derive each of these known equivalences before applying them, in order to be able to do that, that is the reason I said in the last session that you should practice so much that these things come to you very fast, these laws or these equivalences, right? So let's get to it. So in this specific example, in this specific proof, we'll start from the left hand side because that's the bigger expression, like I've mentioned. Now, so the first thing you should be noticing is that there is a negation on the entire expression. The outer parenthesis, the first parenthesis, in the entire expression on this, you have to apply a negation on this entire expression. If you remember, there was a law for that, the De Morgan's law. In case of the De Morgan's law, you see, that is for applying a negation on a certain expression. So if you have to apply the negation on an expression, how do we do that? We distribute the negation, first of all, to each of the variables. So distribute the negation to the variable p and q. So no, you have not p, not q, and the operator in the middle. Whichever operator you have, you invert it to the opposite version. You have or here, it becomes and. You have and here, it becomes or. Okay. So just by looking at this, you should be able to tell that, okay, the first thing I have to do is apply the De Morgan's law. And now we apply the De Morgan's law. Why? Because we have to distribute this negation in order to move to the next step. Okay. So how do we distribute this negation? By applying the De Morgan's law. What's the idea? We first apply the negation to each of the variables inside. Okay. So the variables that are connected with the operator or here are p and another one on the right hand side, which is an expression actually. So you have p on this side and an expression on the other side connected with an or. So you have to distribute this negation to p and this expression, right? So that's why you have not p and then the negation on this entire expression. So negation of this entire expression. And what happens to the operator in the middle, guys? For De Morgan's law?
It changes from or to and.
It changes to the opposite operator. So since we have an or here, it will change to an and. Okay. So there you go. Now that we have applied the De Morgan's law, we have converted this expression to this one. Now, in the next step, if you look at this part here, can any of you tell me whether we are done with De Morgan's law or not? No.
No, we're not done with
আরেকবার করতে হবে
No. In the next step, we have to again apply De Morgan's law, because you see here, the negation on this side, on the right-hand side, is actually on an expression, not on a simple variable. So here, this is on not P, which is fine. We are done with that. And then we have an and. But here, the negation is on another expression. So whenever the negation is on an expression, what do? We apply De Morgan's law again. Okay. So again, apply De Morgan's law. And how do we do that? We distribute this negation to the variables inside. That is, first apply the negation on not P, and then apply the negation on Q. So you have not of not P, that is negation on not P, and then not Q. And what happens to the operator in the middle? It turns into the opposite one. So you may have and here. If we had and, it converts to what? Or, exactly. So you apply De Morgan's law and you get to the second step, this expression. All right. De Morgan's law applied twice. Excuse me. Now, in the next step, what we will do is by just looking at this expression, you should be able to tell that, okay, here, right here in this part, there is a negation on a negated variable. So you have not P here, and on that, you're applying a negation again. So what is this like? This is like minus minus plus, all right? So two negatives make one plus, so one positive. So it's something like that. We have a law for that which is called the double negation law. We actually went over this at the end of last session as well. So since you have an already negated variable inside, and then on top of that you're applying the negation as well, what will happen? Invert of a variable, so you will get P. Not of not P will give you P. Okay. That is just like 1 by inverse of x will give you x. It's very similar to that idea. So apply the double negation law to get to this part. Then, if you look at this expression here, we have two variables in the parenthesis, one variable outside, and then one operator outside and one operator in the inside. And these operators, are these the same operators or opposite operators? Opposite. Remember in the last class we said that if you have something like this, a variable on the outside, two variables on the inside, and the opposite operators are opposite. That is, the operator on the outside is the opposite of the operator on the inside. Then we apply the distributive law. And in the distributive law, what do? We distribute the variable on the outside and the operator on the outside, this whole thing, to each of the variables on the inside. Okay? So this entire thing, not P and, will be distributed to who? To P first and not Q, right? So we have not P and what? Not P and P. And this not P and will also go to not Q. So not P and not Q. So you see not P and. The variable and the operator on the outside is distributed to each of these variables on the inside. So that's why you have this expression and this expression. And this operator, which one is on the one that's on the inside, comes in the middle, all right? So there you have your distributive law. Now, not P and P. What is this, guys? Can anybody tell me what this thing is? This is a contradiction. Very good. This is a contradiction. And a contradiction will always be false. So this is a contradiction. It will always equate to false. So there you have it. Again, not P and P is a contradiction. So directly you can convert this to false and just write down the rest of the expression. That's the negation law. Okay. And also, we've also looked at this. What happens when we have false or some variable or some expression? On what part of this expression now will the truth value depend? Since we have an or here. Remember the definition of OR. So the truth value of this entire expression will depend on what? Can we say that the truth value of this entire expression is false because we have false here? Can we, guys?
No,
No, we
No, ma'am.
can't.
No, we cannot.
because the other
Why?
expression can.
Because it's
Yes, ma'am.
Because the other expression can be either true or false. So basically, you're saying that the truth value of this entire expression actually depends solely on who? The expression on the right side, not P.
On the expression.
Exactly, not P and not Q on this one. Okay, so false or any variable or any expression gives you the variable or expression for which we do not know the truth value. That is the identity the law. All right. So by applying the identity law, we can say that this equates to this one. All right. And you'll see that this is the expression on the right hand side here. So there you go. We
Ma'am,
started
last
from
part
the
side equation.
okay. So all right, whenever we have false or something else, what can we say about the truth value? So okay. So see, P or false, if you have something like this, and we do not yet know the truth value of P, P can be either true or false. If you have something like this expression, this entire expression, what can you say about this? This entire expression is equivalent to P. Why is that? Because by definition of an OR, what do we know? We know that this expression will be true as long as at least one of the variables is true. And it will be false when all of the variables are false. So you have false on the right hand side. You cannot say that this expression is definitively going to be false or definitively going to be true. Why? Because you do not know the value of P. So ultimately it comes down to what? The truth value of this expression, it comes down to what? It comes down to the truth value of P, right? Because there is an R, this false makes no difference whatsoever. This expression, the truth value of this expression depends on the truth value of P. Because this is an R, the false will have no effect whatsoever. The truth value depends on the truth value of P. That is an identity law. Just like when you have P and true, for an AND operation, if you have true on this side, on one of the sides, then the expression, the truth value of the entire expression depends on the variable that you do not know about for an AND. And if you have true on that side. It's just like that. For OR and false, you can say that the expression, the truth value of the expression depends on the variable that you do not know about. Why? Do you understand that? Why we have this situation here? Why this equivalence works?
If there is an OR,
Because it's an OR, exactly. Because it's an OR, even though this is false, you cannot say that the entire expression is false. Because P could have been true, right? Also, at the same time, similarly, you cannot say that it's going to be true because you do not know whether P is true or false. So ultimately, if P is true, this becomes true. If P is false, this becomes false, right? So you see the value of this expression depends on who? Depends on the truth value of P. So can't we say that P or false is equal to P? So that's what it's like. Okay. So go over these equivalences. Try to make sense of these equivalences, these ones, this list and this list as well. Okay, because as you can see from this example here, you have to apply these equivalences over and over again. So here as well, we did the exact same thing. So we had false or some expression. Okay, so we have an or here, right? So false on this side or another expression. So this entire expression, the truth value of this entire expression actually only depends on the truth value of this. If not P and not Q, if the truth value of this expression is true, this whole thing becomes true. If this is false, then the whole thing becomes false. Okay? Does it make sense now? Because false or false is false, false or true is true. So it eventually depends on this expression only. So this is equal to this expression. And this is the one that we had on the right hand side. So we started from the left hand side, move to the right hand side, and there you go, you're done. Okay? So you'd have to know all these known equivalences in order to do these things. Now, so we did this using the truth table. This is also something that comes directly from Boolean algebra. This is something that comes directly from the known equivalences or the laws. Can somebody tell me which specific equivalence or law this is?
Ma'am,
You
the
already
De
applied,
Morgan's law.
exactly, the De
De
Morgan's
Morgan.
law. So this is De Morgan's law. Also, I want you to keep in mind, bear in mind, that this is an equivalence. So you can go to the right hand side from the left hand side, or you can go in the opposite direction. Why I'm mentioning that is that it is not always going to be the case that you have to distribute the negation to the expression inside. It is not always going to be the case like that. You might have some complicated proof where you'd have to look at an expression like this and figure out that, okay, this can be converted to this. What I'm saying is that from the list of known equivalences, remember that you might need to go to the left hand side from the right hand side. Okay. So the example that we did, in that one, it was pretty straightforward. We had something like this, we just distributed the negation. You might have a scenario where you have something like this, negation of some expression and negation of another expression, and from that one you had to convert to this one. Okay, you might just have that. Same goes for this one. Before that, can any of you tell me which law this is? Based on which law we can say that?
Distributive law.
Sorry, distributive law,
Distributive law.
exactly. Distributive law. That's the distributive law. Again, for this one, similarly, here from the left hand side to right hand side is what we did for the example in today's session. That is, in that example, this is how we applied the distributive law, right? So the expression was similar to something that we have on the left hand side, and then we expanded it or distributed the variable and the operator on the outside to the ones on the inside. So we went from the version on the left hand side to the version on the right hand side. However, always remember that that is not always going to be the scenario that you have to follow. In your derivation or in your proof, you might come across something like this, and in order to get to the proof or in order to get to the derivation, you would have to convert something like this to this one. All right, you'd have something. So by looking at this, you should be able to tell, okay, PRQ and PRR. So P and R common. So if I take that outside, P and R, that is P, the variable P, and the operator R is common in both these expressions. So if I take that outside, then on the inside I will have Q and R. So just by looking at this, you should be able to tell that I can go to this side as well. So these equivalences go both way, and you have to always remember that you even from the right hand side, you can go to the left hand side. Okay. So there you go, an example of proving equivalences using known equivalences. Okay, any questions regarding this specific method?
Miss, when we prove the equivalences, do we have to write the name of the laws?
It is recommended, however, you don't have to, but you should break it down to every single step, all right? So you cannot just say, for example, here, what if you decide that, okay, I'll apply De Morgan's law at one go. I would recommend breaking it down to each and every step, all right? Do that. So instead of applying De Morgan's law at one go, what if you might decide to do that? Because this is very easy to do in your head. You can do just some mental math and just apply the negation directly and get to the second step by skipping this part. However, when you're proving equivalences, make sure that you lay out each and every one of the steps. You do not have to mention the laws, but it's good if you do, but you do not have to. So you don't have to remember the names of the laws, but you have to still, nonetheless, remember the equivalences themselves in order to apply them here. Okay? All right. Okay, some of the remarks regarding implications and equivalences, things that we already actually know, by the way. Remember, excuse me, when we were talking about biconditionals, remember, some of you guys pointed out that the biconditional, the truth table of the biconditional, by looking at the truth value of a biconditional, we can tell something about the variables involved in that biconditional. Do you guys remember? What is the conclusion that we can make by looking at the truth values or the truth value of a biconditional about the variables involved? For example, if you have the biconditional between this, if you have this statement, P if and only if Q, By looking at the truth value of this statement, what can you say about the variables P and the variable Q?
দুটাই ট্রু অথবা ফলস হতে হবে, পুরো স্টেটমেন্টটা ট্রু হতে হবে।
Yes. And what does it tell us about the relationship between the variable P and the variable Q?
It means that if P is true, then Q is also true.
I'm talking
অথবা
about the relationship. The relationship. There is a relationship between the truth values of P and Q. If you look at the truth value of the biconditional here, there is a relationship.
They're the same.
Exactly, they're the same. It's when a biconditional is true, what does it mean? Look at the cases when the biconditional is true. If a biconditional statement is true, look at the cases, look at the specific cases when it's true. What's going on with P and Q? They have the same truth values, or in other words, P is equivalent to Q. If a biconditional is true, you can say that P and Q, the variables involved in the biconditional, they are equivalent to each other, right? Or in other words, if the variables are equivalent to each other, then the biconditional is true. So, based on this idea, we have that specific observation. We've already actually got over this. That's what I'm saying. Like, we have some remarks about implication and equivalence. However, we already discussed this or discovered this while we were talking about biconditionals. That is, if you want to prove that P is equivalent to Q, then all you have to do is prove that if P is true, then Q is true. What is the statement, guys? If P is true, then Q is true. What is the statement? What operator does the statement use?
P implies Q.
Sorry?
P implies Q.
Exactly, P implies Q. So A is P implies Q. And you have to prove B. What is B? If Q is true, then P is true. What is this, guys?
Q
Q
implies
implies P.
Q implies
Q
P.
implies P.
Q
So
implies
basically,
P.
in order to prove that P is equivalent to Q, all you have to do is prove that P implies Q and Q implies P. All right? And P implies Q, Q implies Q. Combining these two, what do we have?
A biconditional state.
Exactly, a biconditional. If both of these are true, if both P implies Q and Q implies P are true, then we have a biconditional between P and Q. And if that is true, P is equivalent to Q. As simple as that. Now, in order to prove that P implies Q is a tautology, what do we mean by that? First of all, P implies Q is a tautology. That is, the truth value of this statement, P implies Q is true. That's all it means. P implies Q is a tautology means that the truth value of P implies Q is true. In order to prove that P implies Q is true, what do you have to do? All you have to do is prove that if P is true, then Q is true. That is just by definition, right? That is the definition of an implication. If you assume that P is true, then you have to get to the conclusion that Q is also true. And if you can't do that, get to this conclusion from this hypothesis, that is proof that if P is true, then Q is true, then you can say that P implies Q is true. That is, P implies Q is a tautology. Okay. So we already know about these things. So just these remarks, we already discussed about this when we were talking about implications and biconditionals. Okay, so the same thing here. If A is true, that is, if P implies Q is true, then what do we have? P implies Q are true in which cases? This one, the first combination, second combination, and third combination. However, there is an and. Both have to be true. A and B both have to be true. There is an and. And Q implies P is true. And for Q implies true, P, we have true in the first, second, and third combination. So since there is an and here, we only can take those cases where both are true. So if both are true, we have what here? The first one and the second one. And in both those cases, you see P and Q, they're equivalent to each other. Something that we've already established when we were just talking about biconditionals. So this is something that you already know. Or in other words, if you combine these two, you get biconditional. And whenever the biconditional is true, as you can see, P and Q are equivalent to each other. Excuse me. Okay. Excuse me. So to prove how to
Could you
prove
explain the last part again?
the last part, this part, how we proved that P is equivalent to Q based on the fact that P and Q, the biconditional statement between P and Q is a tautology. This part. What part?
Means these two are basically the
Yes,
same,
ma'am.
right?
Yes, they're the same. This is just one method. This is the other method. In this one, we are going with We are going with the cases where P implies Q is true and Q implies P is true. Look at that. In order to prove that P implies Q is true or P implies Q is a tautology, all you have to do is show that if P is true, then Q is true. If P is true, then Q is true are the cases for the first combination, the third one, and the fourth one. All right. However, there is an and here. We're not just done with A.
Yes, ma'am.
For A, we have three cases where it's true, but that is not enough. We have an and here. We also have to show that Q implies P is true. Q implies P is true for the first, second, and the third combination. So since this is an and, think about the definition of and. We can only take those cases where both are true. All right. So when you show that both of these are true, for the cases where you can prove that both of these are true, P plus Q and Q plus P are true, for those cases, as you can see, P is equivalent to Q. So just by looking at this truth table, we are establishing, we're just simply establishing the fact that in order to prove that P is equivalent to Q, you have to prove P implies Q and Q implies P is true. Okay. And on this side, it's the same thing done in a different way or rephrased, basically. Because if we combine P plus Q and Q plus P, what do we have? A biconditional between P and Q. And the biconditional, if the biconditional is a tautology, that is good enough. If the biconditional is a tautology, or in other words, if the biconditional is true, that is good enough to show that P is equivalent to Q. As you can see, the biconditional is true when? In only those cases where P is equivalent to 2. So in order to, again, prove that P is equivalent to 2, all you have to do is show that the biconditional statement involving P and Q is a tautology, or it's true. Okay? Are you still confused, or was I able to address your questions? Or yeah. Okay,
Yes,
anyways.
ma'am.
So it showed to prove that P is a tautology. I think there was just a implication sign, which is why we're confused. Here it shows biconditional statement. If you could go back to the last slide.
Yes.
So to prove, okay, it says P implies Q is a tautology, then it's sufficient to prove that P is true than Q. That's why it's a little confusing.
Okay, no, this is just about the unidirectional conditional, okay? So don't get confused here. This is a unidirectional condition. It's just an implication, right? That's why if P is true, then Q is true. As long as you prove this, you're done. But for biconditional, you have to go both ways, right? You have to prove both P implies Q and Q implies P, okay? So any more confusions left? Guys?
So
Anybody? Yeah.
biconditionals are always the tautologies.
No. They're not always
They're not
tautologies.
necessarily tautologies.
No, not necessarily. They're not always going to be true. Obviously, they're not always going to be true. However, we are saying that if they are true, in that case, the variables are equivalent to each other. Or in other words, you can say the other things as well. That is vice versa. In order to prove that two variables are equivalent to each other, you have to show that the biconditional between those two variables is a tautology. It's not always a tautology. However, if you want to prove the equivalence between P and Q, you'd have to show that the biconditional between these two variables is a tautology. If you can show that it's a tautology, then they're equivalent to each other. If you cannot show that, then they're not equivalent to each other. Okay?
Okay, ma'am.
All right. Anybody else? Any questions left? Any confusion?
Miss, tautology is like basically the outcome has to be true, irrespective of the.
Yeah.
you take the
Irrespective of
variable.
the variables, the outcome has to be true.
Yes, miss. So for this, we have to go like bidirectional way, like.
If you want to prove that P is equivalent to Q. For any given proposition or for any given values of P and Q, whatever it is, whatever is specified in the given example or in the given problem, if you want to prove that P is equivalent to Q, what you have to do is show that the biconditional between these two is a tautology. That is, irrespective of the values of P and Q, it's always going to equate to true. If that is the case, if the biconditional is in fact a tautology, then P is equivalent to Q, as you see here. However, if you might come across a certain scenario where the biconditional is not a tautology, it's false. And in that case, P is not equivalent to Q. I'll talk about it a little more in one of the examples that we'll do in a couple while. All right. I hope it'll be a little bit clearer then. Okay. All right. I'll do that. Okay. Yeah. This one. I'll talk about that in terms of the specific example. Okay. Excuse me. So we have this compound proposition here, this complex statement which says that P and Q implies P or Q is a tautology. Okay. And you have to prove that this is a tautology. First of all, guys, by looking at this expression, can you tell me which operator will be executed first?
The and
The implication?
and
And
The and the or, right? So by the order of precedence, and or come first, implication comes later on. Very good. So we'll basically execute the implication operator at the end, okay, based on precedence. So based on the implication, we can say that we have one expression on the left-hand side and the other one on the right-hand side. And all we have to do is prove that the statement on the left-hand side implies the statement on the right-hand side. Remember, in order to show that P implies Q is a tautology, in order to prove that P implies Q is a tautology, all you have to do is show that if P is true, then Q is true. That is just the definition of implication. Remember the definition of implication, that's all it is. The conditional statement. What is the conditional statement? What is the meaning of this thing? P implies Q. The meaning is that if P is true, then Q has to be true, right? As long as you prove that P implies Q is a tautology. Okay, so that's what we have here. Instead of just simply P and Q, we have one expression on the left-hand side, another one on the right-hand side. And we have to show that this is a tautology. Now, in order to show that this is a tautology, we have to show that if the statement on the left-hand side is true, the statement on the right-hand side is also true. So here we are asked to prove it using logical reasoning. Okay. So far you've looked at examples of truth tables or node equivalences and such. You might also be asked to prove certain equivalences or prove certain statements using logical reasoning. In fact, that is the thing that we most want to focus on in this course. All right, you'll see over and over again that you're asked to prove something based on logical reasoning. And specifically for this purpose, it is very important that you know about all the basics. All right, you understand. I shouldn't use the term just to know, you understand all of it. All right, it's very important that you understand the basic definition. What is an implication? What is a biconditional? What is an and? What is an or? How do these things work? Okay, so you have to understand these things when it comes to logical reasoning. Okay, because we use those basic concepts to make our case and get to a certain deduction. Okay, that's what we'll do here. We'll just go by definition. First definition is the implication. In order to prove that the implication is true, we have to show that if the statement on the left-hand side is true, then the statement on the right-hand side is true, just by definition. Okay, now what is the statement on the left-hand side? P and Q. So we'll start from here. So our assumption or hypothesis, based on the definition of implication again, the hypothesis or the assumption is that P and Q is true. We can start from that assumption. So P and Q is true. We start with there. What is our task? Our job is to show that by starting from this assumption, we can get to the conclusion that P or Q is true. We'll start from here, start from this hypothesis or assumption, and we have to get to the conclusion that P or Q is true. So this is our hypothesis, and the conclusion is what? That we have to get to, that P or Q is also true. So the assumption P and Q is true. If this is true, think about it. What does it mean for the values of P and the value of the variable P and the value of the variable Q? Focus on the definition of the operator in the middle. And what is the definition of an and of the and operation? By definition of the and operation, what can you say about the truth value of P and the truth value of Q, guys?
Yes, both of them have to be true.
both of them,
Why?
because for like there's an AND operator and all the variables have to be true in order.
Exactly. So this is your reasoning. This is your logical reasoning. See, all of it just comes from the basic definition. An AND operator, the result of an AND operation will be true only when all of the variables involved are true. So if this is true, then what does it mean? It means that P is true and Q is true. Now, if both P and Q are true individually, what can we say about the truth value of P or Q?
It has to be true.
It has to be, it's going to be true. Obviously, it's going to be true. Why is that? Because of the definition of the OR operation. The OR operation gives us true as long as at least one of the variables is true. This would have been true as long as at least P were true, or as long as at least Q were true. In this specific case, we have the scenario where both of them are true. So obviously P or Q is going to be true. Okay. So you see, we started from the assumption that P and Q is true, and from there we got to the conclusion where we see that if P and Q is true, then we can conclude that P or Q is also true. So as you see here, just based on the reasoning that we have discussed so far right now, if P and Q is true, the assumption, if P and Q is true, then P or Q will also be true. And that is good enough to prove that P and Q implies P or Q is a tautology. Because think about it. The definition of an implication is what? If the left-hand side is true, then the right-hand side is true. That is the definition of an implication. And that is what we see here. If the left-hand side is true, then the right-hand side will always be true. As long as the left-hand side is true, as long as the left-hand side is true, the right-hand side will always be true. If P and Q is true, obviously P or Q is going to be true. This is the more restrictive one. If this is true, then this one is obviously going to be true. And that is good enough to prove that the result of an implication is going to be true. Or in other words, this expression is a tautology. The statement is a tautology. Okay. So any questions regarding this proof so far? Okay, if you guys don't have any question, I have a question for you. What if I used a biconditional in the middle? It won't be a tautology, sure, but what if, forget about the expression and whether it is actually a tautology or not, for whatever expression on the left-hand side and whatever expression on the right-hand side, what if we had a biconditional here instead of an implication? And you were asked to prove that the biconditional statement between two expressions is a tautology. What would you have to do then? Would this be enough proving the conditional statement or the unidirectional implication, proving this unidirectional implication, that is starting from the assumption on the left-hand side to the right-hand side? Is this going to be enough for biconditional?
No, we would have to prove it for both directions.
The other way.
You would have to do it for the other side too. That is, you proved the unidirectional implication in this way, you'd have to do it the same thing for the implication in the other direction, right?
Yes.
That is, this whole thing that you've done here, you'd have to do the same thing starting from the assumption that P or Q is true. If P or Q is true, then P and Q is also true. You'd have to do that too. You'd have to do this, fine, but you'd also have to prove that if P or Q is true, then P and Q is also true. Once you prove the conditional in both directions, only then you can say that the biconditional between two expressions is a tautology. However, the biconditional between these specific two expressions, these two expressions, এই দুটো expression মাঝখানে যদি biconditional রাখি, then it is not a tautology. Can anybody tell me why it's not going to be a tautology?
Because we can't prove that if P or Q is true, then P and Q will also be true. Because
Why is that? Explain it.
yeah, because
That is what you have to do in the exam as well. Explain it.
Because
for
of
P or
our-
Q to be true, we only need one variable to be true.
Exactly.
But in case of P and Q, we need all the variables to be true. So there's no
Yeah.
need to prove.
Yes. A little bit more. Yeah, that is correct. You were correct right from the start, but a little bit more detailed or a little bit clearer would be the statement that what you said, that P or Q, if P or Q is true, that is our assumption, right? If you go in the other direction, we'll start with the assumption that P or Q is true. Now we have to consider the cases when P or Q is going to be true. P or Q will be true when both of them are true, yes, but it can also be true as long as at least one is true, just like you said. However, what if one of them is false? In that case, even in that case, it's going to be true, but as long as at least one is false, P and Q is not going to be true. So we cannot definitively say that the assumption P or Q is true will lead to the conclusion that P and Q is true, right? That is what you were saying, right?
Yes, yes, ma'am.
Yes. So because of that, because there might be a scenario, there is a possibility that P or Q can be true without both of them being true, and for P and Q to be true, both of them have to be true. Because of this possibility, we cannot say that P or Q implies P and Q. In this specific case, P and Q implies P or Q. This is fine because P and Q will be true only and only when both is true. However, for P or Q, as long as at least one is true, it's fine. However, if at least one is true, then the other one is definitely false. And in that case, this will be false. So there is a possibility that this will be false even when this is true. So that's why it's not possible to prove the conditional in the opposite direction, right? In the opposite direction, from right to left. It's not possible to prove it in the opposite direction. And that is why the biconditional between these two specific expressions will not be a tautology. Okay? So as you can see, a biconditional is not always a tautology. However, when it is a tautology, the two expressions on the two sides are equal to each other. And again, on the same note, as you can see, the two expressions on the two sides, is P and Q equivalent to P or Q, guys? Is P and Q equivalent to P or Q?
No.
No, it is not. So it's even from that, it's clear that the biconditional would not be a tautology. Or in other words, if it's not as obvious as this, as long as you show that the biconditional is not a tautology, you can say that these two are not equivalent. And if you show that the biconditional is a tautology, then you can say that the expressions on the two sides of the biconditional are equivalent to each other. Okay, any questions left regarding these ideas of conditionals and biconditionals and how to prove these things using logical reasoning? Any questions or confusions left?
Yes, I think we're going to face some problem like writing in details about these logical reasonings.
All you have to do is lay down. Okay, see, every step of the way, I didn't tell you what's going to happen next. You guys told me what's going to happen next. Based on what logical reasoning did you get to the next step? All you have to do is write that down. Okay, think about the definition. Okay, first we start by the assumption that P and Q is true. Why? Because by definition of an implication, if P and Q is true, then we have to show that P or Q is true, and that's when the implication is true. So we start with the assumption that P and Q is true. And then, for the next step, what did we look at? The definition of the AND operation. So by the definition, just explain the definition of the AND operation, and by that operation, what are the things that you can claim? And that's how you progress. So it's all there in your head, okay? Because you are the one who's coming to the conclusion. How did you get there? That's what you have to do. You have to lay it down. You have to write down the steps for that. Okay, how did you get there? That is a key thing in algorithms. For example, when you started with your first basic programming course, all right, I'm sure you had to write some common processes down in steps, break it down in steps. Why is that? Because it's very crucial in algorithm to be able to break down a process step by step in order to be able to see, okay, in detail what happened in each and every step. I did this process, okay, every single day I wake up. But what is the process of waking up? Well, if I asked you to break it down, how would you do that? It's very important in algorithm. That is why we always say that when it comes to logical reasoning, you have to show every single step. You have to cover all bases, okay? So that, and why is that important for algorithms? So that you never leave anything out, that you can be sure that there are no loopholes left. It's very important for that. The things will be a lot easier, I hope, once you start your practices for these equivalences and these proofs and everything using logical reasoning or known equivalences or truth tables. The most people suffer is with logical reasoning, obviously, because even if you get to the conclusion, how do you lay it out? How do you structure it? It becomes harder there. However,
Exactly,
this
miss.
course is all about logical reasoning. So that is actually the most important method. That is the thing that you will most importantly need in the more complex concepts that will come next in your program, right? So that's the thing that you need to practice the most. How do you lay out your logic? Okay. So I've already uploaded the problem sets and the assignments. Go over those problems and go over other problems from the book or other books as well. If you want to go over other books, ask me. I'll suggest other books to you. So you can go over those things and yeah, excuse me. Practice these things out so that in the exam, it's easier for you to express yourself. Okay, generalized or a generalized ad. Excuse me. This is
Ma'am,
just
I have a question.
yes, go ahead.
So, like the compound proposition, like the implication we see on the last problem. So,
Yeah.
like as we know, the contrapositive and the normal implication, they have the same truth values, right?
Exactly.
So, is it logical to think that the contrapositive of the last problem is also a tautology?
Yes, very good. Very good observation. Very good observation. Yes. So what he's saying is that if you remember from the definition of a contrapositive of an implication, the implication is equivalent to its contrapositive. They're equivalent to each other. So if this implication is a tautology, its contrapositive is also a tautology. In fact, you would have to use that in some of your proofs using either known logical equivalences or even logical reasoning. There will be examples where you would have to use this specific idea. Okay, so very good observation there. Okay, generalized or and generalized and. So this is just applying the or operation or the and operation to a generalized number or any number of variables. Just like we've done that for 2 variables or 3 variables, the same thing can be done for any number of variables. You can apply the or operation on any number of variables like this. This symbol here represents dot dot dot. All right. In the exam, it'll be something clear or something very easily relatable, something like a dot dot dot. And what does it mean? P1 or P2 or P3 or P4 or P5 and so on until Pn. For any number of variables, the generalized or of that entire expression is represented in this format. And you also have the idea of the same thing for and. This is a generalized and. And 2 remarks about these things. A generalized or will be true as long as at least one of the variables is true, just by definition of or. And the generalized or will be false only and only when all of the variables are false. The generalized and is the opposite. That is, generalized and will be true as only and only when. The generalized and will be true only and only when all of the variables in the generalized and is true, and it will be false as long as at least one of the variables in the generalized and is excuse me, false. Okay, so the idea of a paradox. What is a paradox? A paradox is any statement whose truth value you can never determine. It's not possible to make any conclusion for that statement. It's a paradox. Okay? Did the chicken come first or the egg come first? All right? So this sentence is false. Think about that statement. This sentence is false. Can this be true? Can this be false? This sentence is false. If this is true, then the sentence is false. Now, if this is false, the sentence is true. You see, it's a cycle. It's a never-ending cycle of possible conclusions, but you actually never get to the conclusion. All right. So similarly, a man says that he is lying. If you're asked, is what he's saying is true or false, you could never come to a conclusion. It's not possible to get to a conclusion. These are examples of paradoxes. Okay. The most interesting puzzles, in my opinion, are the ones whose results are paradoxes. All right. However, in propositional logic, such sentences are not usually considered. Okay. So we're not going to consider paradoxes in propositional logic mostly. But if you think about puzzles, you might come across puzzles. If you practice puzzles like the ones that we discussed in the last session, you might come across puzzles for which the conclusion is a paradox. That is, there is no conclusion. However, we'll try to steer clear of paradoxes mostly to make your lives easier. And in propositional logic, we don't usually consider paradoxical sentences. Okay, now we get to a new concept. Excuse me. Predicates. What is a predicate? A predicate is termed as also a propositional function. And a predicate involves one or more variables. The key word here is variables. What is a variable, guys? What is a variable? Does a variable have one specific value?
No, ma'am.
It could change.
It could change to anything, exactly. So, a propositional function or a predicate function is a statement involving one or more variables, and hence, the truth value of a propositional function or a predicate can never be determined until you specify the value of the variable. The statement, the function becomes a proposition, turns into a proposition only after you specify the value of the variable. Because unless you specify the value of the variable, it's not possible to determine. It's not even, forget about finding out what's true or whether it's true or false. It's not even possible to determine whether it's true or false unless you specify the variable. For example, x greater than 0 is a propositional function. Let's say the statement is represented by px. This is a propositional function. Px is a propositional function, and the variable is what? X. Is this statement true? Is this statement false? Can you determine?
No, miss.
No, we cannot. Why? Because we do not know the value of x. So this statement becomes a proposition which has a definitive truth value of true or false only and only after we specify the value of x. So here, p is the predicate for one variable. Qxy is another example of a propositional function for involving two variables, xy. And it represents the statement x plus y is equal to 2. And similarly to the previous example, this will only turn into a proposition once you specify the value of x and y. Okay, let's say Lx is a propositional function which represents the statement x listens to Lamb of God. However, is this statement a proposition? No, because you cannot definitively say whether this statement is true or not unless you specify the value of x. Whether the statement is true or false depends on the value of x. So this will turn into a proposition only after you specify the value of x. Okay, so before then, it's not possible to find out whether it's true or false. No idea. So this statement here, this propositional function representing this statement, excuse me, is not a proposition. That is, there's no way to find out the truth value of this statement. X is termed as the subject, and this part here, the rest of it here is termed as the property of the subject. So L is the predicate representing listens to Lamb of God, which is the property of the subject. Okay. Now Lx is the value of the propositional function L at x, and will have a truth value only after we know the value of x. For example, if x represents some person, Amy, and this person listens to Lamb of God, then what does it mean? The truth value of the statement now is going to be true. Amy listens to Lamb of God. It's true. You can assign a truth value now based on whether this person listens to Lamb of God or not. Amy listens to Lamb of God. True. Amy does not listen to Lamb of God. False. Right? So based on the value of x, you can determine the value of the propositional function at x. Similarly, some other person, maybe they don't listen to Lamb of God, then it will equate to false. Another person listens to Lamb of God, it will be true. It's just like if I talked about this entire class here. If x can be anybody from this entire class, whether the statement is true or false depends on who that person is, right? Unless you specify the person, you can never tell whether the statement is going to be true or false. So unless you specify x, it's a propositional function at x. Once you specify x, it turns into a proposition which has a definitive truth value of either true or false. Any questions so far? Okay, let's do some another example then. Now, let's talk about another propositional function. This predicate function at xyz, which represents the statement y is equal to x plus 2z. All right. So here, y is equal to x plus 2z. This statement, guys, is this true or false?
We're not sure because there's
Why?
We're not sure.
We need the value.
Exactly. Unless
That is
we
the
specify the
unspecified.
values of x, y, z, it is not possible to even determine the truth value of the statement. Hence, this is a function, propositional function, which represents the statement, but it's not a proposition yet. So here x, y, z are the subjects, and n is the predicate, and x, y, z will have a truth value only after we know the values of x, y, z. So it turns into a propositional statement once we specify x, y, z like this. For example, in x, y, z, this statement here is a propositional function. And 3 to 1, however, is a proposition because now we have specified the value of the variables 3 to 1. If you apply these values here, you have 2 on the left hand side, and on the right hand side it's 5. Is 5 equivalent to 2? No. So for these specific variables, is this statement true or false, guys?
false.
False, exactly. So once you specify the variable, you can say whether
Miss, we can't hear you.
all right, guys. Sorry again. As you can see, we are having a plethora of problems today. I don't know why. Yeah, some days are good, some days not so much. Once again, we're back online. Can everybody see the presentation?
Yes, yes.
Okay. So let's get back. So here, so this quantification is another way of finding or converting a function into a proposition for which we can determine the truth value of. All right. So let's see what is it. So first we have the universal quantifier. The symbol for that is this inverted A, this vertically inverted A. This is the symbol for universal quantifier, and it stands for the term. The way we read it is for all. And when we have something like this, we read it like for all x px. Remember I was talking about a domain? In case of quantification, the concept of domain goes hand in hand. For example, for the previous case, for example, for this example, if I said the domain of X is this class for discrete mathematics, autumn 2020, section 4, this class is the domain for X. What does it mean? The values of X can only come from this class. That is the people who who are represented by this X are the people, only the people in this class, not outside of this class. So X can be anybody from this class and only within this class. Okay, so that is the domain here. Now, when we use this expression here for all X Px, it means that for all possible values of X in the domain, for all possible values of X in the domain, Px is either true or false. For this expression, for all X Px, for this expression, for all X Px to be true, Px has to be true for every single value of X in the domain. Okay. For example, look at this statement here, this one. This is a propositional function, right? What if I said that the domain for xyz is the set of all integers? Is this statement going to be true for all possible integers? Guys, what do you think?
No.
No, it's not going to be true. So the universal quantification of this statement for the domain of all positive integers is false. Okay, so you see, we didn't actually specify xyz to one specific combination. We just specified what? The domain. In case of quantification, just like here, just the way you have to specify the specific values, in case of quantification, we have to specify the domain. The moment we specify the domain, we can determine the truth value of the universal quantification of a certain propositional function. All right, existential quantification. The other one is the existential quantification, and the symbol for that one is this thing that looks like an E, the horizontally inverted version of an E, a capital E. So this is the symbol of an existential quantification. I don't know what the Greek or Latin fancy word name for that is. I'm sorry.
Why can't we just write E? Like, why do you have to invert this?
Because that is the symbol for this one. All right. So all of these ideas. See, the reason we have this. Why do we have pi? The symbol for pi. Why do we have psi? Why do we have these things? So the mathematicians who came up with this concepts, it all depends on the origin of that mathematician, the language that mathematician uses. Okay, so based on that language, actually, usually these things come. Somehow the symbols always come from Latin or Greek. In case of physics or math, you'll see that most of these come from So okay, so this is the symbol for existential quantifier, and no, you cannot use a simple E for that. You have to use the symbol because this is the symbol that is used in mathematics to represent the existential quantification of a propositional function. Okay, and this is read as there exists. So if we have something like this, we read it as there exists an X such that Px. That is, there is at least one value of X in the domain for which Px is true. Okay. If that is the case, then the existential quantification of this propositional function for the given domain is true. If that is not the case, it's false. So do we understand what I'm saying here? So the domain, for the same domain, you can say that this existential quantification for the same proposition is true as long as there is at least one X in the domain for which the propositional function equals to true. Let's look at the same example. For the same statement and for the same domain, what is the domain again? The set of all positive integers. For the same statement, the existential quantification of this statement for the domain all positive integers, is that going to be true or false? The domain is all positive integers for all of xyz. Is the quantification, the existential quantification, good or false, guys?
True. Yes, I think it's true.
It's true. Okay. Why do you think it's true?
Because there will be some values for which this.
There may be. Don't we have examples already here for which this is true?
Yes, miss.
Sure, there are examples, other examples for which this statement is false. However, For existential quantification, what do we need? We need at least one example, at least one case from the domain for which the statement is true. As long as you have at least one, the existential quantification is true. For universal quantification, all of them has to be true. That's why the universal quantification was false for the given domain. But the existential quantification is true as long as there is at least one. Okay? Is it clear now to everybody? For the given example, for all the universal quantification for the same domain is going to be false and the existential quantification is going to be true. Anybody has any question regarding that?
No.
Okay.
No.
All right. So basically, what do we understand? We understand that for all xpx is actually equivalent to the propositional function at x1 and the propositional function at x2 and the propositional function at x3 and x4 and x5 and so on until xn. That is, if this is true, the statement on the right hand side, that is, if the propositional function is true at all of these values of x from the domain, see x1, x2, x3, x4, x5, so on until xn. That is all of the x's. If the propositional function is true at each and individual one of these x's, only then the universal quantification is going to be true. So true if and only if all. So this is equivalent to this, the general and. True if and only if all are true. And for the existential quantification, what do you guys think? What will we have there? The operator.
Or operators.
Or operator.
Very good. Why is that?
Because at least one has to be true.
One.
Exactly. As long as at least one is true, it's going to be true. Very similar to the idea of an or. So, and false only if all are false. So, existential quantification can be represented in this format. The domain of discourse. The domain of discourse, we've already talked about that in our discussion about quantifiers. The domain of discourse is the set with respect to which we determine the truth value of the quantification. Okay, so whenever we have a quantifier, the domain will be specified. Unless you specify the domain, you cannot determine the truth value of the quantification. Just like here, you have to determine, or just like here, you have to specify the values of xyz. In case of quantifiers, you do not have to specify the values of xyz to 3, 2, 1 or something like that specifically. However, to determine the truth value of the quantification, you must specify the domain. Okay, what is the domain? Based on the domain, you can tell whether the truth value of the quantification, universal or existential, is true or false. Okay, the domain, that is the possible values of x or the allowed values of x. So it's all possible values of x from the domain. Usually the domain is assumed to be non-empty. Why is that? Why is the domain assumed to be non-empty? Because think about what happens if the domain is empty. For all xpx, what is that? The universal quantification. What does that say? It says that this will, as long as the propositional function is true for each and every value of x from the domain. For all possible values of x from the domain, if the propositional function is true, then the universal quantification is true. Now, if the domain is non-empty, now if the domain is empty, in that case, what do we have? There is nothing in the domain. There's absolutely nothing in the domain. So by default, we can say that yes, for all values of xpx is true, because there is nothing in the domain. For all values of xpx px is true. For all possible values of x from where? From the domain. So if the domain is empty, that by default makes the universal quantification true. All right. Think about what happens when the domain is empty for existential quantification. What is the definition of an existential quantification? When is it true? An existential quantification will be true as long as at least one value of xpx is true. You have to find at least one value of x, at least one, for px is true. Can you find even one value of x in an empty domain? Can you? No, you can't. If the domain is empty, there isn't even one value of x there. It's empty. So that's why the existential quantification for an empty domain will be false by default. So that is why usually it's assumed to be non-empty. Okay. If it's empty, however, these for the universal quantification is true by default and the existential quantification is false by default if it is empty. Some of the important sets of numbers that you need to know about, some of the sets that will be commonly used in quantification for domains. All right, when we talk about quantification, we always specify the domain, right? And for the domain, some of these common sets are often used. The set of all natural numbers, the set of all integers. However, instead of the set of all natural numbers, we'll actually use the term set of all non-negative integers. Why is that? Because as you see here, in this specific case, in this specific demonstration, we have shown that 0 is there in the set of all natural numbers. However, this idea is debated. Some mathematicians say that 0 should be there, some say that 0 won't be there. So we will not use natural numbers most often. Instead, we will use the set of all non-negative integers to represent the same set. What do I mean by that? Think about it. The set of all integers consists of all negative, positive, and 0 integers. Okay? All the negative integers, all the positive integers, and 0 are there in the set of all integers. What about the set of positive integers? Is 0 going to be there in the set of all positive integers? No. Is 0 going to be there in the set of all negative integers? No. The set of all positive integers starts from 1 and goes on. The set of all negative integers starts from -1 and goes on. So 0 will not be there in any of those sets. However, if we talk about the set of all non-negative integers, 0 is not negative, so 0 will be there. So the set of all non-negative integers starts from 0 and keeps on progressing with all the positive integers. So the set of all non-negative integers contain 0. Okay? Any questions?
Miss, if you don't mind, can you just explain the domain again?
The domain of discourse.
Yes, Miss. I'm just a bit confused.
Okay, so domain of discourse are the allowed or the possible values of x. So we are saying, let's say for example, this one, the universal quantification of this propositional function. What does it say? For all x px. For all x, that is for all possible values of x, px is true or false. All right? For all possible values of x. Now, these all possible values of x comes from where? From the entire universe? From the entire world? Where does it come from? All possible values of x from a certain domain. Let's say, for example, if I say that the domain is the set of all integers, then what happens? Then this universal quantification for the domain of all integers will be true only when the propositional function is true for all integers. Okay? All the allowed values of x come from where? From the domain. Once you specify the domain, you can tell whether the quantification is true or not. You have to specify the propositional function, you have to specify the domain, and you have to use a specific quantifier either for all or existential. Okay? Same goes for the existential quantification. At least one of x px. At least one x, at least one value of x. X এর ভ্যালুটা আসছে কোথা থেকে? X এর ভ্যালুটা, the boundary, the set from where x is coming from. What is that set? That is the domain. Okay? The possible values of x. That is the domain. So in order to determine the truth value of quantification, of any kind of quantification, the domain must be specified. The domain can be something like this: the set of all integers, or the set of all positive integers, or the set of all negative integers, or the set of all non-negative integers. We'll look at some examples. Think about this again then, and if it's not clear even then you can ask questions again. All right? There's also the set of all rational numbers. That is also a commonly used set to represent domains. A rational number is a ratio of two integers. Any integers represented as a ratio is a rational number. Then you have the set of real numbers, which is any number that can be represented on the number line. Then you have the set of irrational numbers. For example, √2 pi, the exponent. All of these are irrational numbers. So yeah. So what we do is, for quantification, we determine the truth value only after the propositional function is given like this. For example, here x greater than 0 is a propositional function, right? and the the propositional function is mentioned, and the quantifier, the specific quantifier that you're going to use, universal or existential, which one? We specify the quantifier, as you see here. The universal quantifier is here. And finally, we specify the domain. Only after you specify these things, which specific quantifier you're using, what is the function, and the domain, after that, you can determine the truth value of the quantification. Okay. For example, here, we want to find out the truth value of this function, the universal quantification, sorry, the truth value of the universal quantification of this function, x greater than 0, for the domain that consists of all real numbers. If the domain is all real numbers, x can be any value from this set, as long as it's from the set of real numbers. X can be any real number. The domain being the set of all real number means that x can be any real number. Now you have to answer, is x greater than 0 for all real numbers? Yes or no?
No.
Why?
Because x is 0, minus 1, minus 2.
Real numbers consist of negative integers.
Exactly. There are negatives in real numbers and 0. And for these cases, x is not going to be greater than 0. So universal quantification of this function for the given domain is false. Because in order for the universal quantification to be true, it has to be true for all possible values of x from the domain. Okay. Now, what happens when the domain is changed to the positive real numbers? What happens then?
X is greater than
That
0.
is true.
It's true.
It becomes true. Why is that? Why? Because by definition of a positive number, of a positive real number, by definition of any positive number, we know that that number is going to be greater than 0. And that is our function here. So for the domain that consists of all positive real numbers, this the universal quantification of this function is going to be true. See, the truth value changed the moment we change the domain. You see? So there. Okay. Now let's look at the function x equals to 0 and the existential quantification of this function. For the domain that consists of the set of all integers, is this going to be true or false? Is x equals to 0? Can you find at least one example of x equals to 0 where the domain for x is the set of all integers? That is, x can be any integer. Can you find one example of an integer which is equal to 0?
Yeah, 0.
0, exactly. 0 is there in the set of all integers, right? 0 is there in the set of all integers. And that one example is enough to make this existential quantification true. Because for existential quantification, all we need is at least one x from the domain. However, when we change the domain to the set of all positive integers, you cannot find even one value of x from this set, the set of positive integers for which x will be equal to 0, right? Can you give me any example of a positive integer which is equal to 0?
No.
No, why? Because 0 is simply not there in the set of all positive integers, right? So there is not even at least one. So the existential quantification of this function for this domain is going to be false. Counterexamples. What are counterexamples? For universal quantifications, what did we say? The universal quantification is going to be true only when the function is true, equates to true for all possible values of x from a given domain. However, it will be false as long as there is at least one x for which this is false. See, for this case, the first case, for all real numbers, all you have to show is just one example. Just one example. X equals to -3. For x equals to -3, this is false. -3 is a real number, yes. So it's from the domain. So it is a possible value of x. And for -3, this function is not true. So, yes, there are other examples. Yes, there are other examples for which this function is not true. There are also other examples for which this function is true. But we're not concerned about that because by definition of a universal quantification, As long as there is at least one x for which this is false, the whole thing becomes false. Okay? So that one example that you're going to use, to disprove a universal quantification is the counter example. All you need is just one example. For example, for this function here, for all x greater than 0, x equal to 0 is a counter example for the domain of all real numbers. For x equals to 0, 0 is a real number. And for 0, this function is not true. 0 comes from the domain, and 0 is a possible value of x. And for that, we see that this is not true. And that makes the entire universal quantification false. That one example is enough. There are other examples for which this is false as well, yes, but all you need is one. So the example that you are going to use to disprove a universal quantification, if you can do that. If it's true, it's true. It's true for all values, fine. However, if it's false, if you think it's false, the one example that you use to disprove a universal quantification, that is termed as a counter example. Okay, so we'll stop here and pick up with some more examples in the next session. So the first class next week we'll do some more examples of universal quantifiers and existential quantifiers, and the things will start to get even the things will get clearer in the next class. And also, I would like to remind you that you should keep going over these lectures because we haven't had a quiz yet. All right. So it's either going to be the Wednesday of next week because we'll be done with, I'm guessing we'll be done with the quantifiers by next week, hopefully. So it's either going to be Wednesday next week or Monday the week after. All right. So make sure that all throughout you keep preparing yourself by trying out the problems from the assignment and trying out the problems from the problem sets. I'll stop the recording here. If there are any questions, you can go ahead and ask.